Okay, so now we are going further, and today we consider hyperreals. So non-standard real numbers. So hyperreals say x element of star R. Now, once again, what is a hyperreal in plain words? Take care. Okay. What is a hyperreal? You have a index set I and filter f, and now you consider all sequences. So x is say f of I, I in I, f of I in R. So consider all the real valued functions, or if I is, for example, just integer, positive integer, then it is the set of all sequences. And you define, no, it's not f, we consider this f, and consider the set mf. It is a set of G, such which maps I into R, such that G of I equals f of I almost everywhere. Yes? So it is equivalence class of sequences, or generalized sequences, G. And X is this class. Yeah, so this is non-standard real number, or I will call it hyperreal. Now, in particular, if f of I equals say x0 almost everywhere, then x, let us write simply, is at 0, x is a standard number. Yeah. So the constant, or everywhere constant, almost everywhere constant sequences form the image of this, I would say, immersion of standard numbers into non-standard numbers. And for non-standard numbers, we define, as usual, the arithmetical operations. We define relations like inequalities. So all in the usual way. Now let me define x in star R is called, let me call it bounded. If corresponding x equals mf, like here, and module fi less than some c almost everywhere. So in this case, I call it bounded. So it is bounded. I would not call it finite null because it looks like a bounded sequence. Yeah? So it is a bounded number. And now I give another definition. X is called infinitesimal if x less than epsilon for any epsilon in R and epsilon positive. So here x element of star R. Yeah. No, strictly speaking, we have to write here star less, because less is a relation in star R, so it is already non-standard extension of relation less. Yeah. No, for example, suppose I equals n. The simplest case, I is n. And consider f of I equals, say, 1 over I. It's enough. Then consider x equals mf for this f. Yeah? Then for any epsilon, we can take I more than 1 over epsilon. Yes, and then f of I is less than epsilon. And our ultrafilter f is a non-trivial ultrafilter in the sense that any finite set, finite subset of I has measure 0. It's not element of ultrafilter. Yes? And so this means that that model f of I less than epsilon almost everywhere. Yeah? No, and in the sense of this relation, this means that x less than epsilon. Yeah? So this is example of a number which is infinitesimally small. Okay, and so now we have the following natural, I would say, partition of the hyperreal set star R. F, let me use different, F is ultrafilter. Yes, okay, so A is the set of finite, of bounded X in star R. So we have A. We have B, the set of unbounded X in star R. unbounded means not bounded. And let us introduce the set J, the set of infinitesimal x in star R. Okay, no, we have obviously A and B gives all star R. No wonder in this, and we have that J is a subset of B. Of course. Now let us look at this, first of all, at this set J.
Meaning A, right?
Excuse me?
Do we mean A? Like J is included?
J bounded A. Yeah. J is already an interesting set. J is an interesting set. So, suppose that x and y in J, then it is more or less obvious that x plus y, x minus y, x times y, all in J. Now, which is more or less obvious. Now what we can do else, we can multiply some number of J and some number of A. So if A in A and X in J, then what we have, it is also more or less obvious, then A times X also in J. So J is, I would say, ideal in the ring A. Yeah? Now if, say, B in B capital, then it is not the case. So just A. Now in particular, if A in ordinary R, and ordinary R consists of finite numbers, so they are bounded. So ordinary R is in star R, it's not interesting, it is in A. Yeah? Star R is consists all of bounded numbers. Then AX also in J. Now if you combine this and these things, we have the following, that J is a module over R. Vector means linear space such that its elements can be multiplied between one another, and at the same time they can be multiplied by numbers, elements of R. It is a model. If it is a model, so it is first of all a linear space. What is the dimension of this linear space? Yes? Claim dimension of J over R is infinite. That means that we can find arbitrarily many linearly independent elements here. Yeah? No, in fact, let some epsilon in J. Yes? Then say epsilon, epsilon square, epsilon cube, and so on are linearly independent. Or R. No, why? No, okay. Let me, maybe somebody can give me the proof. No, say why epsilon and epsilon square are linearly independent. Suppose for some C1, C2 in R, C1 epsilon plus C2 epsilon square is 0. Yeah? No, okay, we can divide by epsilon by the transfer principle, nothing changes. So this implies C1 plus C2 epsilon is 0. Yes? But this C1, if it is 0, C1 is 0, then C2 is 0, by the same transfer principle. If C1 is not 0, then C1 is no bounded number, first of all, and not in J. So in A minus J. C2 in C2 epsilon. Epsilon is element of J. C2 epsilon also in J. Yes?
Is this C1 epsilon or C2 epsilon?
Excuse me?
Is this C1 epsilon or C2 epsilon?
It is not epsilon, it is element of. Yeah.
Oh, sorry.
This epsilon, this is
Oh, yeah.
inclusion. Yes. Yes, there is a problem. There is a problem. No. Okay, so we have that one element C1 is not in J, C2 epsilon is in J, which is contradiction. Yeah? Yeah. No, okay, so similarly you can take any number of terms here, and they all are linearly independent over R. So we see that this has quite interesting construction. And I think it is a good question if somebody is interested to describe maybe what is the real structure of this set G as a linear space. No, there is more than one infinite dimensional linear space, so what sort of it? Does it have some structure? Can it be given, say, topology or something like this? Is it, God forbid, a Banach space? I don't know. Yes, so it is possibly not an empty question. Certainly it depends on our model of our ultrafilter, but nonetheless, can something interesting be said about this object? Okay, so this is one thing, and let me introduce one notation. That if x in J, we denote it x is approximately 0. No, I think we have more than one notation for the same thing, but the thing is quite important, so let it be. Yeah. Now a small question. J is a set. So the question, is this set internal or external? What do you think?
External.
Huh?
External.
External. Sure, it is external. So what does mean internal set? Internal set is a set which is itself an object of our non-standard universe. Yes, and this is not this is not. It is simply a set, but this set is not element. Yes. So Y is not an element. Why it is not an element?
I guess we could prove it saying like it's bounded above, but it doesn't have a supreme on.
Yes, yes, like this.
Something
Like this. No, okay. And what about the set A of bounded numbers? Is it internal or external? Bounded numbers. Again, it is external set. The set of bounded numbers is not element of our universe. Again, why? If it were element of our universe, so what it may be? It is a set. Yes. So there should be a sequence, for example, of sets, of subsets of R, yes, and this set is equivalence class. Okay, let us do the following. It is a little bit advanced question, yes? So let me explain it separately and maybe not in the lecture. Yes, possibly it is better to write it down and then you will have because it can require a little more effort. But the important, this is important fact that this set is external. Now, the next thing, I want to describe the structure of the set star R like I did last time with star N. Yes. So, to this end, I formulate a theorem. Theorem is the following. For any bounded star R, there exists some A in R such that X minus A equivalent to 0, or X equivalent to A. This is the same. So this means that X minus A is infinitesimally small. So it looks like crazy, because what is a bounded number? It is, no, materially it is a sequence. No, if, say, our index set I is just integers, it is any sequence which even is not bounded. It is bounded almost everywhere. And almost everywhere means that, for example, at every second step, every second term, yes, all terms with even number, may be arbitrarily large, maybe grow as they wish, because simply the set of even indices has measure 0. Anyway, if it is not measure 0, it measure 1, then odd indices have measure 0. Yes, because we have ultrafilter. And so we have arbitrary set, it can oscillate as it wish, arbitrary sequence. Yeah? And nonetheless, there is some sensible number A, real number, just standard real number, such that this sequence is, in our sense, infinitesimally close to this number. Yeah? So we have to recover this number somehow. And here, let me explain how it is done. So let me do it twice. First, I will explain it without transfer principle, or this transfer principle, some elements of this will be parts of the proof, which is not long. And second, I will do it with transfer principle. So, the proof. Proof 1. Let us, so what does it mean? For any bounded number x in R. So x in A, yes, means that there exists some C in R plus are positive numbers, such that in this continuation f of I absolute value less than C almost everywhere. Let me write x equals mf, first of all, and f of I is such a function. So now let us take some particular f, anyway all other functions, representatives of this class will differ by on a set of measure 0. And so consider the segment from minus C to C, and here we have 0. And let us define I 0 equal set of I such that f of I less or equal than 0. I1 is the set of I in I such that f of I more than 0. No, let me write minus C less than f of I less or equal than 0. F of I less than f of I less than C. So it is clear that these two sets are complementary, and so one and only one of these sets has measure 1. Other has measure 0, and we can neglect it. So suppose that I say I1 is this set. Measure of I1 equals 1. Now we define two sets. I1 equals I1 0 union I1 1. To this end we divide this segment from 0 to C into two subsegments. From 0 to C over 2, and from C over 2 to C. Yes? So I one of I such that less or equal than f of I, less or equal than C over 2. I1 equal a set of I such that C over 2 less than, here simply less, f of I less or equal than C. Yeah? And again, the total measure of union of this and this, or measure of I1 is 1. Yes? And so, because of finite additivity of this measure, one of these sets has measure 1, other has measure 0. So, suppose the measure of I, say 1, 0 is 0, measure, okay. One measure of I1, 1 is 0. Yeah? So this means that we should consider only the indices I such that Fi is on this segment, which is a quarter of initial segment. And all other i's which were the corresponding terms are in this and in this segment are negligible because their set has measure 0. Yeah? No, now we can continue on and on. We divide this in 2, so you see it is very familiar to the proof of some standard theorems in analysis. Yes, so we go on. We have a family of, say, nested segments like this. Yeah. So going on and on, we get a family of nested segments. Let me denote this segment, say sigma 0, containing sigma 1, containing and so on. So this is sigma 0, sigma 1, sigma 2, sigma 3, and so on. Yes, and the length of these segments goes to 0. Yeah. Length of sigma k goes to 0 as k goes to infinity. So by classical lemma or theorem, I forgot the author, there exists one point in common of these segments. By the say classical theorem, is it really classical? Who knows this? Please, who knows this theorem? Raise your hand. Okay, so it is classical theorem. There exists unique A in intersection of sigma k, from 0 to infinity. Yeah? And now we can see, so this point A is somewhere here. This is the point A, which is in the intersection. And now you see that almost all of the terms of this sequence are, first of all, all of them are in sigma 0. Now almost all are in sigma 1. Almost all are in sigma 2. Yes? And so on. So for almost all terms, the difference between A and the term lying in the corresponding segment is bounded by the length of this segment, because both points are in the segment, and this length goes to 0. Yeah? So this means that for almost all I, for almost all I, let me write, for any epsilon, for almost all I, in our index set, we have f of I minus A less than epsilon. But this means, if you return to our definitions, this means that the following. Which means that x minus a less than epsilon. So again, for any epsilon, we prove that first. So in this order, there exists a such that for any epsilon, the difference x minus a is less than epsilon. Yeah? No, here to be in the same universe, x in star r, a is in r, but the r is also in star r. So they are in the same set, we can compare. Whew. Yes, so this is one theory, one proof. Other proof. It somehow recalls another classical construction, which is the Dedekind construction of real numbers by sections. No, to be closer to Dedekind, consider the set of rational numbers. It is a subset of R. And let's observe the following thing. Suppose we given x. In star R, x in A, which is A is a subset of star R. A is the set of bounded numbers. Now, suppose we have R in Q. Then we can we have the following, I would say, the following three possibilities. We can say that let me write here. I would say one and only one is true. First, x equal r. It can happen. Then no problem. If x equal r, so we have a rational number, which is a real number, which is infinitesimally close, namely the distance is exactly 0. Second, x less than r. And third, x more than r. Yeah? So why we have only three possibilities? For example, if x were ordinary real number, then this is a theorem. So any two real numbers are comparable by this. Yes, and then by transfer principle, it can be transferred to star R. Now, the first is, then we are done here. If x is less than r, 2, then r in, let us denote with, say, t plus. If 3, then r in t minus. So t plus are the rational numbers, the set of rational numbers which are more than x. T minus is the set of rational numbers which are less than x. Yeah? So it can be called upper class and lower class. T plus is upper class, T minus is a lower class. And so, if x is not itself element of Q, yes, if S is not element of Q, then only this or this can happen. So this means that Q equals T plus union with T minus. Any number in Q is either in the upper class or in the lower class. And next we have, if x in T plus R and T plus and S in Q S more than R, then S also in C plus. Because in this case R more than X, S more than R, so we have transitivity in ordinary numbers, and the same holds for non-standard numbers, so by transfer. And similarly, if R in T minus, T in Q, and T less than R, then T in T minus. Similarly, if R less than X, T less than R, then T less than X as well. Yeah? So for ordinary numbers, no, it is what should be proved. For this number, it's also proved. This is called transfer principle. So what? Yes, and every time we have to return to definition of these objects as equivalence classes of sequences, and go step by step and prove that it is true. So also by transfer. Now, this is the setup for the Deakin's construction. Do you know what is the Deakin construction? Who knows what is the Deakin's construction? Okay, so setup. So if you have the set of rational numbers, and this set is divided into upper class and lower class, so that this holds, that if a number belongs to upper class, then any larger number belongs to upper class. If it belongs to lower class, then any smaller number belongs to smaller number. Then this is called the Deakin section of rational numbers, and by definition it defines a number. Yes? And then this number can be identified with a number which is defined in any other way. Say as equivalence class of Cauchy sequence, for example, or as finite or infinite decimal fractions with identifications. Yes, by contact. So it is, let's say, so let me write. So Q equals T plus union T minus is the defined section defining unique real number A. That's it. This way we found this number. Now, no, that's it. What? It remains to prove that A is the number which is infinitesimally close to X. So, if X is more than A plus epsilon, yes, then T minus is not a lower class. Because between A and A plus epsilon there are also rational numbers which are also in the lower class. So if X less than A minus epsilon, then T plus is not the upper class. I mean, there exist other numbers which are not in this T plus. That's it. So, model X minus A less than epsilon for any epsilon. No, you can fill in details yourself. And so we have let me now introduce the crucial notation. Given X in A, we denote the number A such that X minus A belongs to J. We denote the unique number A in R. A equals standard part of X. So we have a non-standard number, and somehow we extracted from this number a standard part. No, for example, if X is infinitesimally small, then A is 0. So we somehow erase this delicate fine structure and have this very material thing. Yeah. So this is a notion of standard part. And what happens if we want to find the standard part of a number which is not bounded? Which is not bounded number. If x is in start r minus a, yes, then this construction cannot even begin. Yeah, so it makes no sense. Then we define standard of x is an empty set. Yes, please.
Wouldn't we like say something like standard part x is infinite plus or minus infinite, depending on
Infinity is not standard object. Yes, so I prefer to say that there is nothing standard in a number which is infinitely large. Yes, and in fact it makes more sense because in what follows I'm going to define standard part of any object in non-standard universe. So some of them have standard part, some do not have. Yeah. Okay. And this without model. So we have the following: A is a real part. A is a real number, x is hyper-real, yes, and A is a unique real number such that x, let me say, x equals A plus epsilon, epsilon equals x minus A, and this element of J. It is infinitesimally small. Yeah? And so we have the following thing. Any x in A can be uniquely written as x equal standard of x plus epsilon. Epsilon in J. Here we are. And now, what we see in the non-standard line, we see something fantastic. Non-standard real line. So we see the following period. First of all, we have something which we call A. Here in the middle is 0. And in this A, we have real numbers. And for every real number, we have the set standard of x plus epsilon. If epsilon runs over all J, let me introduce one more term here. We have to somehow call this. and this is a very beautiful name for the following thing. The set A plus epsilon, such that epsilon in J and is called a monad of A. So A is a standard number. It is monad. What is monad? It is a term invented by Leibniz and has some deep philosophical meaning, which I am not ready to explain, but the name is very beautiful. So we have monad. Yeah. So the set. So first of all, the set A contains standard numbers, standard real numbers, and around each standard real number there is monad. Let me call this monad, monad mu A. It's notation. So we have a point A, and here we have some monad mu A, the center of A. And as I explained you from our ordinary viewpoint, this monad is infinite dimensional vector space. So we have some this infinite dimensional vector space, which is somehow put here in infinitesimally small neighborhood of A. And for any A, we have this. Now we know that different real numbers form a dense order. So between any two numbers is another number. So there is no next number. Somewhere here we have, say, B, and around here is monad of B, and so on, but there exists continuum of this standard number between A and B. And this is A. This is the structure of the set A. Now, as for other parts, I think it becomes really fantastically transcendent, and I cannot describe it now. I think it depends a lot, enough to say that as a set, it can have arbitrarily high cardinality. Depends on our index set and ultrafilter. Yeah? So it is something transcendentally complicated, but nonetheless we have to work with it. Sometimes we can. I hope to reach some point where I can show some examples where it is useful. Okay. So I think it is a good point where to stop today. Because next goes, what goes next? Next we'll study non-standard extension of sequences, then non-standard extensions of functions. Yes, and then maybe extension of things like metric and topological spaces. Okay? And we have a lot of wonderful things there. So cu